Welcome everyone. It's a great pleasure to have Tim presenting today, one of our associate investigators. We're very fortunate to have, we like in Optima not only to engage with industry partners, but to also engage with colleagues on our own campuses who have optimization challenges that are juicy and interesting. And Tim is one such person. So Tim is a professor in the Faculty of Science, recently awarded an ARC Industry Fellowship, the university's first and only. And I guess what he's talking to us today is related to his big research agenda, and no doubt related to also some of the stuff that he's working with us on in Optima, where we have two projects with Tim as a supervisor of two of our students, Yi and Vaughan. I see Yi here, I can't see Vaughan. Yeah, thank you, Tim. Do you want to share your slides and
all right,
get us started?
I will indeed. Just check. Okay, great. All right, I'm assuming everyone can see that. Yeah, it looks like you can. So yeah, thank you very much for the introduction, Kate. It's really a pleasure to be here. And before I start, I'd just like to acknowledge the traditional owners of the country on which I'm very happily seated, particularly given how beautiful it looks in this weather, which is the Waterway people. And I'd like to pay my respects to their elders past and present, and kind of acknowledge the insights we get from their sustainable management of lands and water and landscapes over many, many years. It often strikes me that we managed to achieve a level of degradation in just a couple of hundred years that they did not achieve in 50, 60,000 years. And that's much to our great shame. But anyway, so I'm going to talk a little bit about the concept of a smart rainwater grid, where we use technology, and this is where we kind of intersect with the need for optimization, the use of technology to bring the environment and people and money together. So that might seem a little bit obtuse, but hopefully I'll take you back to the start, back to the kind of history, and then get to that destination at the end. Okay, so I'm kind of sad not to be there in physical person. I've got another meeting at 6 that means I can't, but because I would have liked to do a kind of classic raise the hands if type scenario. So here you see a picture of a waterway. This happens to be the West Moorabool River, which flows between Ballarat and Geelong, essentially, a part of Ballarat and Geelong's water supply. If I asked you to raise your hand and tell me if the local stream near you looks like this, if any of you are raising your hands, I suspect you have a very long commute into the Parkville campus. It's unlikely that if you live in and around Melbourne, your streams look like that. They're more likely to look like this one on the west. Okay, Charlotte does. I'll find out later where you live, Charlotte, in approximate terms, so as not to sound creepy. It's more likely that the stream you live near, or the closest stream to you, looks like the one on the left, perhaps eroded, so that one's out at Mount Evelyn, or looks like the lined Mooney Ponds Creek, or even worse, looks something like this. And you might ask yourself, well, whose fault is that? Whose fault is it that the streams in urban areas look so degraded? And I'm going to start provocatively by saying it's your fault, actually. It's your fault because you choose to live in a house that has a roof to keep your carpets dry, and you choose to likely have a driveway that's made of concrete or something like that, so you don't get bogged, and then likely to have a bitumen road outside your place. All of these things that make urban life kind of more comfortable, but also result in a complete change to the way water moves through the landscape. So you'll see in that picture a little kind of hole here. hydrologists or stormwater engineers like myself would call that a side entry pit, as in it's an entry for stormwater on the side of the road. And all of the water that runs off that road goes into that pit and then ends up in the receiving waterway. That changes everything. So rather than the vast majority of water in the natural landscape being evapotranspired back up, so evaporated by by the atmosphere essentially, or transpired by vegetation. So the same process, but through plants, through their stomata. Instead of that vast majority being evapotranspired back up and the rest of the water infiltrating into soils, in the urban context on the right, we basically get a complete reversal. So around 85% of, I don't know why that's happening. I've got my phone switched off. About 85% of the rainfall ends up as runoff, so going over those impervious surfaces and then straight into the waterway. So you can imagine the waterway is going to be affected by that. It's now got a much, much bigger flow in it, so it's going to have to enlarge, as in it will start to erode and enlarge. But we also see a loss of water in the water table, so lots of things start to change. If we look at some work done by my colleague Matthew, as I see he's here, he did some work showing how significant these changes are. So if we look over on the right, we see that the flow regime is much more peaky, big flashy responses to rainfall. So these two streams are both in the sort of outer eastern suburbs of Melbourne, experiencing the same rainfall. They're right next to each other. One is urban and one is not yet urbanised. Probably will be, but not yet urbanised. So the urban one has much more flashy response, but we also see on the bottom of that graph, the black band is that base flow or that dry weather flow. So the flow that's basically trickled through the soil, being filtered through the soil and ends up in the stream. That's really depleted in the urban context. That makes sense from a physics point of view because we've now sealed all the surfaces so that water can't get into the sponge that the natural soils are. And so there's nothing to replenish that base flow. So if you're an organism that lives in the stream, and here I'll use pure unadulterated emotional manipulation to convince you of the importance of this topic. This is a little baby platypus. The term for a baby platypus is a puggle, in case you didn't know. If you're something like a platypus, or indeed the macroinvertebrates or little bugs that platypus need for their food source, then you've got a choice now in that urban environment. You either get washed away by a big flood every time it rains, or the flow is so depleted that you don't have enough wetted habitat to live in. So not surprisingly, we see very rapid and substantial degradation of waterways. So someone called Chris Walsh coined the term the urban stream syndrome, basically explaining all the changes that occur to urban streams and basically concluding that you lose their structure, you lose their habitat, you lose their biodiversity, you lose their ecosystem services. There's nothing but bad news in there. So over the last couple of decades, the concept of water-sensitive urban design has different terms around the world, but aims to reduce those peaks and restore that base flow using a range of kind of bioengineered kind of concepts. So putting in place systems in the landscape that mimic what naturally would have occurred. Of course, we can't ask you to remove the roof off your house so that it's now, permeable, etc. But we can do things like rainwater tanks that will hold back that water, things called rain gardens that allow that rainwater to go into a kind of garden and then soak into the soil, or wetlands, etc. We can engineer things that mimic those natural processes. And so these kind of concepts that promote infiltration, promote filtration, promote evapotranspiration by the vegetation, and very importantly, promote harvesting. I'll focus on that particularly because one, that's very important to reduce the overall volume of runoff, remembering that the runoff has gone from 15% of the annual rainfall to 85%. So, you know, a 4 or 5-fold increase very commonly. So we need to reduce that volume. Harvesting is a very effective way of doing that. And it has a very powerful other argument, which is it adds to the water supply security. We are already in Victoria having early discussions about creation of additional desalination plants, which will increase the energy cost and the financial cost of water supply through the network, particularly in the western side of Melbourne and down to Geelong. So there are already government level discussions on this, looking at future droughts. The potential of harvesting stormwater is one cost-effective and environmentally effective way of reducing that requirement, because we can harvest that captured runoff. So a big group of us, including my colleague Matt Burns and I, and led by our colleague Chris Walsh, who's just retired, set about with support from lots of agencies, including the Australian Research Council, but particularly with Melbourne Water, our closest collaborator over the last 20-odd years, set to see whether we could apply these water-sensitive urban design technologies and improve the stream, get the stream back to a healthy state. So we spend a lot of time building a lot of systems. We paid, or our partners paid for a lot of these systems to be built, but actually Matt and I and our colleagues actually spent a fair bit of time on shovels and excavators and all sorts of things, building things as well. We built some 300 of these systems around the catchments that we were interested in restoring, or the streams we're interested in restoring, and we measured their change over time in terms of hydrology, so flow through the streams, and water quality, and we compared those to streams that we didn't do any work on, or catchments, so the areas that drain into the stream, that we didn't do any work on. So this was what's called a backread experimental design, before, after, control, reference, impact. So we measured before for many years. We did about 15 years of building these things, and we measured during that time, and then we measured after, and we measured the other catchments as well, so that we could assess whether there was a change. And to do that, we obviously had to work extensively with the community, because a lot of the land is private land. If we want to deal with the runoff from someone's roof, we need to be working with them. So we use some novel kind of economic instruments, reverse auctions, etc., to fund that work. We, as I say, spent about 15 years on those interventions, about $10 million, and we did monitoring throughout that time. So just to have a look at a couple of metrics of performance, here are 4 of our study catchments, and I want to particularly focus on this one, LN, which is a Little String Dark North. It was the catchment where we were able to do the most works. Now, I'll just explain what this chart is looking like. On the x-axis, it's the size of the rainfall event during a particular storm. And on the y-axis, we've got the maximum observed flow, which is the number of millimeters of observed flow, so millimeters spread over the catchment. So area standardized flow rate in a 6-minute time step, because that's how we measure. The reference catchments are those forested catchments that they're not urbanized, they're natural, they've got nice trees, etc. So up in the Dandenongs, where we would expect that they act in that natural way of being like a sponge that retains the rainfall rather than causing runoff. And sure enough, you see that there's a very muted response to increased rainfall. Sure, you're getting some runoff when you've got 48 mil of rain, as you'd expect, but it's not a big response, very, very muted, noting the scale of the y-axis. On the yellow band here represents what we call the control catchments, so the catchments which are urbanized and for which we did no works. We didn't try to, we didn't implement any of these water-sensitive urban design works. And the grey band represents the source control measures, so where we put stormwater control systems in. And so this work done by Matt shows that particularly for small rainfall events, we've managed to restore what we would call its retention capacity, so its ability to absorb rainfall without producing runoff, so absorb it in the soils, etc., or absorb it in our systems we've created, is pretty close to natural. Once we get to bigger rainfall events, our systems are overflowing and contributing to discharge, and so they start to be overwhelmed, essentially. That's kind of what we'd expect. It's good news. It says that we were able to get some level of restoration. So these techniques clearly work. But if we look across for big rainfalls, they could be better. And some of our other study catchments, they also could be better. The levels of improvements are not great. If we look at our water quality results, so same sort of structure here. In this case, we're looking at total phosphorus, which is a nutrient, but also a pollutant. It contributes to algal blooms, which end up causing, toxic blooms that will kill fish, kill people if they happen to be particularly affected too. So we want to try to reduce the amount of phosphorus going into streams. Again, it shows that our works have been somewhat effective in doing this, but we could have gone further. And I show the paper here led by Chris Walsh, which publishes this work. All right, so I actually wanted to focus more on the but than the results here. Why the but? Why were we not able to achieve as much as we would have liked? Well, first of all, despite having money to pay people to participate, we didn't really get as much participation as we needed. We kind of ran out of money, and some people weren't interested, or at least weren't interested in at the money we could offer. We found that quite a few of the systems malfunctioned over time because they weren't maintained. So, for example, we installed a lot of rainwater tanks with pumps, and we would often find that up to a third of them, either the inlets were blocked or the pumps weren't operating, and the owners didn't even know. We also found that, for example, during winter, when there's not much demand from water from those tanks, they would be overflowing, so they're not doing what they're meant to. And then in summer, they get drained down, but during winter, they're not so effective. And we found that the community relatively was pretty passive. Once they installed these systems, they didn't think about them because there was no kind of incentive for them to think about them. While we're working on that, Matt and I were starting to get very interested in this concept of real-time control technology, the idea where we could use real-time control of elements, these kind of elements, throughout the catchment or the network, and control more optimally the flow of water, the holding back of water, the treatment of water, etc. And we started to think about how that could overcome some of those problems of maintenance and malfunctions, because you would know when it wasn't working, you'd be getting a signal telling you, and how potentially we could even tap into a more powerful financial model, which I'll come to later. So we started through a PhD study undertaken by someone called Wei Xu, who played with this concept of multi-objective control for rainwater tanks, where these tanks are being used for water supply, but also being controlled in a way that reduces their risk of overflowing, so reduces the risk of flooding, and releases water to the nearby waterway in a sort of steady basis in order to restore that base flow that's been lost from the streams. Remembering that point I made, that we're not getting infiltration, so we're not getting that replenishment of the groundwater, which is what feeds the streams with water during dry weather. So we think, oh, well, we can engineer that back with this type of real-time control technology. And so this technology essentially uses a Bureau of Meteorology forecast, so a connection to that forecast. We're using the Australian Digital Forecast Database, ADFD. We're receiving a live feed of that twice a day. And then we are making decisions about releasing water from that tank if a storm is forecast, because we want to create airspace to contain the rainfall that might go in. But we're also making decisions over a longer time, perhaps a week, to release flow at a given slow flow rate to provide that, sustain that base flow into the stream. And so with Way and assisted by Kate, we started exploring how to optimize these tanks, and we played with different strategies for controlling these tanks. We're using a 7-day rolling forecast. So we have the Bureau for we have the Bureau's forecast for 7 days, and we make decisions to release based on that 7 days. And each day we update that forecast with the new information available to us from the Bureau. So we're constantly adjusting our releases. So if we, for example, determined that we needed to do 700 litres of release in the next 7 days for a storm event that was coming in 7 days, we would make 100 litres release on the first day and then see what we were told by the Bureau the next day. And we tried different scenarios that focused more on protecting against floods, more on providing base flow restoration, but these were all rules-based type approaches without an optimization component initially. We then looked at how we could optimize across a network rather than simply making each tank work individually. So having a sort of centralized control where each tank knew the status of every other tank. And so, for example, I might have a small tank, but Matt might have a very large tank. And so my tank will know that essentially it can rely on Matt to pick up the slack when my tank is empty, for example. And we found we're able to achieve quite significant, quite useful gains by that coordinated type control. And we collaborated with some colleagues in Quebec, in Canada, who had a catchment where there was significant flooding in their sewer system, so their pipe network. And we applied these approaches, combining with some sort of industry standard modeling tools called SWIM, in order to deliver a flood reduction outcome for that catchment. And that the City of Quebec is actually implementing some of these works as we speak, so really encouraging. So by this stage, we're starting to think, yeah, there's really some potential in real-time control for networks of, in this case, rainwater tanks, to improve the way stormwater is managed and potentially help improve our streams. And so we started getting interested in, okay, from what we know, from all the work we've done working with the community and how vital they are playing a role, because after all, 50% of the impervious surfaces that we're trying to deal with, the surfaces causing runoff, are on private land. Sure, there's roads, etc., and that makes up about 50%, but the other 50% is all your roofs, essentially, and a little bit of footpath, etc., but particularly your roofs. And so we launched this project where we aimed to explore using a network out in Monbulk, where we've got a whole lot of houses, and you've also got some large existing storages, so Belgrave Lake, Monbulk Creek, or Birdsland Reserve, where we could apply this technology at this scale. And one of your excellent PhD researchers, Yi Zhen, is working exactly on the optimization here, and where we aim to see how we can optimize the flow regime, in particular for the platypus. There are 16 platypus in that stream, threatened species, really important species, one of only 2 monotremes in the world. I don't need to go on. Working at how we can protect that species is absolutely vital. So we've built at this stage, we've built a network, or we're building a network of all of these tanks and the large storages, and we've written some control software to operate this whole network, including a user interface. So each of the tank owners can have a look at their contribution and optimize how they operate it. This is informed by some quite detailed science about what flow regime the platypus needs. In this case, you could do it for other species, for fish, etc. We're particularly interested in the platypus. And so we understand in a quite detailed way what type of flows we need to deliver at what times of the year to, for example, enhance its breeding success. All right. So just as an example of how our rules-based code works, we basically read the stream flow each day. We make decisions about whether that's adequate, whether it meets the sort of minimum flow requirement. If not, we calculate the release that's required. We identify all of the storages in the network. We ask them how much water they have available. So essentially, we're doing that through an API, application program interface. And we're doing this across multiple authorities. So this is run on a Melbourne Water server, but connecting to a Southeast Water server who run all the small tanks. We ask each tank how much is available, including what reserve level they want. In other words, what proportion of the tank do they not want us to go near, because that's the water they want for their toilet or their shower or their car washing or whatever. And then we make releases from each of those tanks according to some rules. And we have a component we call Mars bars in the desert, where we, depending on how full those tanks are, we scale the releases down, because we would rather make smaller releases over multiple days rather than one big release over one day, because we're looking to sort of sustain a flow for the platypus. If we don't need to make that release to provide a minimum flow for the stream, we simply check with the Bureau forecast, is there a need to make a release in order to avoid an overflow, because there's a big storm coming today, and then we'll make that release if we need to. So we run these two bits of code together. So that's how we currently do it, using this simple rules-based algorithm, which we call Mufasa. So Melbourne University Flow Allocation Simplified Algorithm. Clearly, we came up with the acronym before the definition. But Yi-Zhen is working. Yi-Zhen is working in a much more sophisticated way to develop an optimization approach to this. So rather than simple rules-based, which, to be honest, work well most of the time, but certainly perform non-optimally and can get caught out. So Yi is working on an optimization that considers the reduction in flood risk, maximizes the water supply relative to the demand, so the yield relative to the demand, and also tries to keep the minimum flow within a band. So that base flow restoration is trying to keep within a certain band. We don't want too little, but we also don't want too much. It's no longer base flow if we do that. So it's always trying to keep itself within that band. And in order to make sure that the system operates as stably as possible and doesn't get caught out by future conditions that we don't yet know, it tries to, in F4 and F5, tries to maintain the system as stably as possible. And it's using, again, as I talked about before, a 7-day receding horizon control. So we're always looking at 7 days and then adjusting each 7 days. And so Yi, whose contact details and photo are up there, has been doing computational experiments to identify which of the strategies is most effective. And so she's meeting, for example, with Melbourne Water each week and talking to them about results, and they are making decisions about which way they want to go. This is the interface of that system. So the user interface, so the owners of the tanks see this. They can make changes to their tank. They can decide how much of the tank they allocate for use by the project or by essentially by the platypus, compared to how much they want, etc. And they therefore have fairly active communication with us about, what impacts they're having and what contributions they're making. Okay, so where are we going? And Kate mentioned the most kind of recent funding we've had through this industry laureate scheme. The aim here is really to build a smart stormwater or rainwater network that's inspired quite simply by the same concept we use for distributed electricity. So here we have, the concept we all know very well. You're connected to a grid. You receive electrons from that grid, essentially. You receive also electrons from your own solar panel to supply your house. When you have an excess of electrons, those go back to the grid, and you are paid, albeit not a lot, paid for your contributions to that grid. And so that is part of your investment decision and also part of your operating decisions that you make each day. Now, water is a different thing. Water is a lot heavier than electrons. I doubt I needed to tell you that. And so the way it needs to be operated is differently, but the basic concept still has some appeal. So we can reward essentially, or pay the owners of these tanks throughout the network for their contributions to reducing flood risk, and also their contributions to protecting the stream, essentially protecting the environment of the stream. The economics of this are interesting because an organisation like Melbourne Water has a legal responsibility and indeed collects a rate to pay for its works in protecting waterways. And in theory, rather than them directly spending that money all the time, they could be paying, in the same way as we pay solar panel owners, paying owners of these rainwater storages to make some of that contribution to protecting the stream. And that's indeed why Melbourne Water is a partner in this project. They are interested in whether this could be a kind of least cost way of achieving protection of waterways, particularly in new development areas, new suburbs. So over the next few years, hopefully continuing to collaborate with OPTIMA, this is really where we want to go. We've got quite a bit of interest from South Australia Water, so in Adelaide, and also from in Melbourne, where they want to apply this on sort of pilot scales of 500, 1,000, 2,000 homes, and see whether this could be a future way of providing a sort of decentralized water grid in the same way as we have a sort of hybrid centralized, decentralized power grid. All right, I will stop there and happily take any questions.